Hey everyone, welcome back with a new lecture with Accredited Laboratory. This is training course about quality control, quality assurance, and in the previous lectures I have explained all things about errors and all type of errors and some case studies also relating to the errors. In this lecture I will just give some points or new understanding about the difference between errors and uncertainty, because this is very important point. Errors which refer to the difference between measured and the true value or real value. So if the spike sample concentration should be 10 microgram per kilogram as example, and you got 8 or 5 or 3, so there is a bias or deviation from the real concentration. This deviation equal to the whole errors found in the whole analytical process, and these errors should not affect the accuracy of results. You should control these errors so it will not affect the accuracy of results. So errors bias from the true value and affect the accuracy of results. If the errors are high, the accuracy will be low. As I explained before, that accuracy, closeness of results together and to the true value. If the errors are high, so there will be bias, high bias between the real concentration and the measured value, and this bias will affect the accuracy of results. So the results will not be close to the true value, so accuracy will be low. And calculated like this: bias equal to true or reference value or real concentration minus measured value. And bias percentage, when you estimate the trueness during your validation process, you will calculate bias percentage, which is equal to reference minus measured value divided by reference value multiplied 200. And measured value here, not only one value, because you will make repeatability. So you should make replicate analysis of a spiked sample or sample spiked with known concentration, or CRM, certified reference material, as I explained before in the method validation course. So you will calculate the average between the whole replicate analysis that you will do. Then you will calculate bias percentage, which is equal to reference minus average divided by reference multiplied 200. That estimate the trueness. If the bias is low, bias percentage is low, that means the results are accurate and the result near to the true value or real concentration. So it's very important to eliminate or reduce the errors to be able to get accurate result at the end. Accurate result doesn't mean that you should have 100% same like the real concentration, but you should have acceptable range based on the guideline that you use, as I explained before, from 70 up to 120 percentage the recovery, or relative standard deviation less than or equal to 20 percentage, or according to the guideline you use. You should follow this acceptable range. Within this range your results are accurate. Higher than this range or lower than this range, your results are inaccurate. So you should try to assess the errors during the whole analytical process and try to reduce them so your results will be within acceptable range. But the measurement uncertainty is the range, not only one value, but you will have acceptable range for your sample concentration, the range within which the true value or real concentration expected to lie, taking into account all possible variations, all possible errors and variation. So there is a value should be quantified, which is the measurement uncertainty value, should be quantified and added to the final result to compensate all effects coming from every step of the analytical measurement. So measurement uncertainty is a value. This value should be quantified. You should quantify this value, should be quantified to be added to the final result. So you should add measurement uncertainty value that you will quantify to every analytical result. Every result for every sample concentration, you will add the measurement uncertainty value for each analyte to the final result to compensate all effects coming from every step of the analytical measurement. Any effect on the result will be calculated, will be quantified and added to the final result, so it will compensate, and you will get at the end the real concentration within acceptable range. As I said, the range within which the true value or real concentration expected to lie. So if we need to differentiate between both of them in a table like here, errors, definition, deviation of measured value from the true value or real concentration, measurement uncertainty, range is the value added, but range at the end, range within which the true value expected to lie. And here type, systematic or random, that we explained before, errors, and here account for all possible variations during the whole analytical process or measurement. Direction, that can be positive or negative, but when you calculate bias percentage, you will calculate a bias in a positive result. Bias, positive result. At the end, it will be positive result. And here expressed as confidence range. Confidence range. So at the end, you will write the final result for the sample concentration, 10 microgram per kilogram as example, plus minus 2 microgram per kilogram after you calculate the measurement uncertainty value at confidence level 95%, and that we have been explained many times before. So expressed as a confidence range. And impact on result, that can lead to biased or incorrect result. If it's high, if you have more errors, it will affect the accuracy of results and can lead to biased or incorrect result, should be eliminated or reduced. And measurement uncertainty, no, measurement uncertainty value added to the final result. So you should quantify and get this value to add to the final result for each analyte. Will be quantified for each analyte and get a value. This value will be added to the final result to get a range, acceptable range for the real concentration for your sample. That was the end of our lecture for today. Thank you and see you in the next lecture.